did a great job and I assisted him. The edges of the graph, all the vertices and the edges, in a way that the cost would be the lowest. Okay. We saw some examples of drawing different types of minimum spanning trees, right? There can be many minimum spanning trees for a given graph. Okay. Now, when I made that statement, I thought somebody would ask a question, and it skipped my mind too. What happens if all the edges are same weight? Would we have one unique minimum spanning tree? Or would we have many minimum spanning trees? Think about that. Okay. So that was all the background, and then we did a quick brief through in terms of saying that, hey, what else is going to come in this particular chapter? One of the things we talked about when we flipped through the slides was Kruskal algorithm and Prim's algorithm, right? Those are other techniques too. And I said we'll keep covering these things over the next few weeks. Okay, so that's the background. So what we'll do today, we'll start off with this exercise for minimum spanning tree. Okay, what the problem is asking for is there are 5 towns. Okay, this is very apt for Jntuk Kakinada. Whenever ASN Garu has to make a round trip to all the colleges, he has to figure out what is the best way to traverse all the colleges for any kind of presentations, right? So the cost of construction of a road between towns I and J, Aij. Ij is the subscript. I didn't have time to format it. The subscript. So here are 5 towns, right? You can call them A, B, C, D, E. So if you see A11, obviously it will be 0 because you are in the same town, right? If you go A to B, the distance is 3. A to C, the distance is 5. A to D, the distance is 11. Like that, you read that. Okay. Is there anyone who does not understand how to read the matrix? Very straightforward, right? So just call these towns A, B, C, D, or you can give real names if you want to. It's up to you. Okay. Your exercise right now is to find the minimum cost road network connecting the towns with each other. Okay. Is there anyone who does not understand the problem? What the problem is asking for? Put it in the chat. If you don't understand, put it in the chat. I'm trying to move my window so that way I don't block. Okay, looks like all of you understand it. Mentors, give groups of 2 again. I want you to solve this problem. Find the minimum cost road network connecting the towns with each other. Okay, how you do that? I want you to think. It's obviously a minimum spanning tree exercise. So what is the first thing that you do? Take this matrix and then convert it into some kind of a tree, I assume. And once you convert that into a tree, then you know how to get to a minimum spanning tree, right? We learned that. Take 10 minutes for this exercise. Faculty members, please help them make progress on the exercise. If anyone has any questions, put them in the chat and I'll answer. 2, and then 2 to 3. Okay, so let me do another C control V there. So I'm assuming you are seeing my screen. 2 to 3, right? So you have a line connecting. Where are the lines? So you have 1 to 2. Okay, there's a line there. Let me change the color of it. Okay, and then you have the same thing 2 to 3. Somebody else got 3 plus 3 plus 10 plus 7, 23, yeah. Okay. 21 is the right answer, by the way. And then you have a similar thing from 2 to, why I didn't get it. Okay. I got this. Then I want to, so 2 to 3, assuming you have a line there. And then I'm saying 2 to 5. So you have a 2 to 5 also. So if I do Control C, Control V, let me call it 5. There's a line there. For some reason, I'm not able to select the line. No clue why I'm not able to select the line. There it is there. Okay. So I have a 2 to 3 line. Oh. Come on, I selected the line and it did. Okay. Shape outline, same thing, black. And then I have a 2 to 5 line. Where do my lines disappear like that, just like that? Shapes, design. Insert, okay. The lines keep going from one shape, one place to another place, like that. And then I have 4 to 5. So I should have some 4 here somewhere, another node. So if I put 4 here, so I had a line going from 4 to 5. Like that. Okay. So 23, good effort. Now, is there anyone who does not understand it? I hope all of you did some practice, right? What? Problem, right? You're given a matrix, but a matrix can be redone as a tree. That's what we have learned, right? So you drew some graph there. You basically put 5 nodes. And then whenever you see 1 to 2, there's a 3, right? So you draw a tree. 1, 2, 3, 4, 5. You take each of the lines and then you draw a line whenever there's a value and then put the value there. Right? From that, you figure out the minimum spanning tree. Okay, that's good. Now let me go to the presentation mode here. Okay. Now last time we showed this slide saying that, hey, these are the algorithms that we typically talk about for greedy. Dijkstra's algorithm for finding the shortest path in a graph. Okay. So, and the way it works is it always takes the shortest edge, connecting a known node to an unknown node. Now, that sentence does not mean anything unless you practice, okay? Now, Kruskal's algorithm, it does it in a way where it focuses on lowest cost edge. So it's an edge-centric algorithm. Whereas Prim has another way of doing it, where they do it in a slightly different way, where they still maintain the spanning tree and they consider vertices. I mean, they still take the lowest cost edge between nodes, okay? But the edge which is not yet in the spanning tree is what they focus on. So we'll take a look at these things and we'll work through some examples today, okay? Pencils, I hope you have a lot of papers. Faculty members, you have to facilitate this, okay? We are coming up with an exercise in a couple of minutes. So Dijkstra, when we talk about Dijkstra's algorithm, we are basically talking about a single source shortest path problem. Okay. So how do you define the problem? The problem is finding shortest path from a source vertex. So that means there's a starting point, okay, to all other vertices in the graph. Okay. So if you are given a graph like that, let's say your source is 6 or maybe 1, wherever, right? Your goal is to find the shortest path from that source to that vertex for all the vertices. Okay. Let's see what happens here. Okay. So I freely borrowed the slides from one of the nice presentations that I liked. This is actually from a UT Austin presentation. As I shared with you, I actually went to UT Austin a long time ago, and I had an opportunity to see Dijkstra, listen to his lectures, and all that good stuff. A nice set of slides. I just copy-pasted them as is. Here is the famous Dijkstra. Okay. And a very nice quote from him. Computer science is no more about computers and astronomy is about, oh, no audio. The 1972 AM Turing Award, and that is equivalent of Nobel Prize. The Nobel Prize for computer science is, excuse me, vector graphs. Okay. Only thing is, all of them should have non-negative weights. Okay. The approach itself of the algorithm is greedy. Okay. So you have an input. Since it's graph, graphs have edges and vertices, right? That's why this is the symbol that we use. G equal to E comma V. E is for edge, V is for vertex. And then you're given a source vertex V, which obviously belongs to the overall set of vertices. Okay. So output is length of the shortest paths, okay, from a given source vertex to all other vertices. Okay. If you actually look at the railways, Indian Railways distance maps, it kind of shows something similar. If I'm not mistaken, go check out the Indian Railways website. How does the algorithm work? Here is the pseudocode for that. Okay. I'm not explaining that. I'm just showing that to you. Okay. On the left, you see the pseudocode. On the right, you see the explanation. Everyone gets it? Very straightforward, right? You can see distance to S, what S means source, and for all the vertices in V minus S, right? Because S is the source. So you're doing what? Do distance of V equal to infinity. That means you're setting all the distances to infinity. Similarly, rest of the code. Okay. Since you did some preliminary programming and I showed you some programming examples for you, you should be able to understand this pseudocode. Okay. Now what do we do with this? Okay. Get ready now. Okay. What I want you to do is trace Dijkstra's algorithm for this graph. Okay. Faculty members, if you have a board there in your classroom, please feel free to write this graph on the board. Or students, you can write it on your piece of paper. Okay, notice the arrows and all of those things. Pretty simple graph. You shouldn't take more than a minute or two to write it down on your piece of paper, all of you. And faculty members can write on the board. And you can see there's a Q there. You can write exactly what you're seeing in the slide deck here. Okay. So you have A, B, C, D, E. Remember the first step that he was doing here? For all V belong to V minus S, do distance of V equal to infinity. That is what we have done here, right? Under B, under C, under D, because source is A. Okay. And A is 0. Because A to A is 0. Everything else is infinity. See how they are marked here. Infinity, infinity, infinity. Okay? Everyone understands that? Is there anyone who has questions on that? That's important. You need to understand how this is going to work now. Give me a holler on chat that you have finished copying this on your sheet of paper or on the board. Then I will move forward. The Q there, which was empty, right? I think was it Q which was empty or S? S. You'll start filling out the set. Okay? So just keep following the code. Fill that out. 10 minutes. Okay? And if somebody just had the same slide, yeah, I just want to see. Yeah, I had a copy there. Okay, great. So applying the algorithm. So 7, 9, all infinities there. Okay, now you see how the set is going to be built up. So what is S? What is S containing? Can somebody tell me? You can see AC. Okay, now you can see how the table Q is changing. See the values, how they are changing, right? So AC is in the path. Somebody put AC, I think, right? Did somebody put AC? Yep, AC3, some Jntuk Kakinada, they did that. Good. Then we have ACE. Did anyone put ACE? 3 plus 2, 5. Yeah, A equal to 5. They put that. Excellent. You got it. Okay. Then what do we have? ACEB. ACEB. A to B, right? Now, while you're doing that, see how the infinities have changed to the actual values. Right? And the last one remaining is D, right? Excuse me. And you get the last one, D there. You can see how the chart got filled up there. Okay. Very neat, huh? Dijkstra, how he did that, and he showed the paths there. For those of you who have not completed it, I would recommend that outside of the class also you work and make sure you are able to do it. Because it's a beautiful, beautiful algorithm. As I mentioned to you earlier, Dijkstra was able to figure this all out in his mind in 15 minutes, sipping coffee in a cafeteria. Okay. Now, whenever we have these algorithms, we always want to see the complexity, right? That's what we started off this subject on. Okay. So how do you do that? You typically save them in either an array or a linked list. And you can see the running time is of the order of V squared plus the number of edges. Okay. If the graph is sparse, you can optimize it a little bit. Okay. Where we'll use an adjacency list. Somewhere along the way in this course, I talk about adjacency lists and adjacency matrices. Okay. And then we use what is known as a binary heap or a priority queue, where the order would now become order of E plus V log V, which is much better than V squared. Okay, log is good, remember? Now, okay, I pressed something accidentally here. Give me a second. Okay, so this is the analysis that was there. I'm skipping the analysis because I want the students to go through this couple of slides and see how we came up with those things, right? For example, it gives very clearly why something is order of 1, right? So you can convince yourself about that analysis, okay? Because you have the algorithm, right? So go back to these bullet points, map it to the algorithm, and then convince yourself that that analysis is indeed correct, okay?
Okay, what do we have next? Okay. Next are these two things, Kruskal and Prim. Okay. One relies on vertices and one relies on edges to come up with the basically what we just did. Okay. So we'll see some good slides again for that. Okay. So this is the Kruskal's algorithm. Okay. Select the shortest edge. So it is edge centric, right? And then step 2, select the next shortest edge which does not create a cycle. So you cannot have a cycle. That is a tree. Remember, tree does not have cycle. You are given a graph. You are trying to come up with a tree. So obviously you cannot have a cycle. Okay. And you continue that till all the vertices have been connected. That's what a spanning tree is, right? That you should have all the vertices. Okay? Looks pretty simple. That's what this big slide on the back is. That edge-centric is Kruskal's algorithm. Okay. So that means start with the collection of single trees, each with exactly one node. Right? You start applying this algorithm. That's all we are doing there anyway. Okay. That is Kruskal. Now this is Prim. Side by side. Okay. In Kruskal, you started off with edge. In Prim, you're starting off with a vertex. Okay. Big difference, right? One is taking the shortest edge. The other one is taking any vertex connected to that vertex. Okay. And then step number 3, select the shortest edge connected to any vertex already connected. Okay. So you're building one tree. Okay. And then you are in step 3, which you continue to repeat until all vertices have been connected, because that's the end goal, right? All vertices have to be connected. Okay. Now, I think I have a animation of this, I think. Yeah. So here is an example. A cable company want to connect 5 villages to the network, similar to the example that you already solved. It has A, B, C, D, E, right? You wanted to travel, here you are connecting. Okay. So what is the minimum length of the cable needed? Distance, basically, right? So see how these things play a significant role. Whenever you talk about cables, it could be telecom networks. You could apply to waterways if you're channeling water to different towns, right? So many applications of this. Okay, so here are all the towns, 5 villages, right? Obviously some European villages. The distances have been given, or length of cable, whatever you want to call it. Okay. So that is nothing but a network. How do you find the minimum connector for the network? Minimum means again minimum spanning tree, right? So here is Kruskal's algorithm. If you apply the Kruskal's algorithm, what are all the edges that are there? Remember, we are starting with the lowest edge. So you list down all the edges first. Okay, increasing order, because we start off with the lowest one, right? So ED equal to 2. Okay, that is step number 1. Step number 2. What is step number 2? Next edge, I think, right? Next lowest edge, I think, AB. But we have to check that there is no cycle. So where is AB here? AB is there, so it's going to make it red. See, ED, AB. See, they are being highlighted in colors, okay? Then CD. I want to monitor the chat if somebody has put anything. Yeah, Sri Prakash said also up to n-1 edges, sir, when n is the number of vertices. Absolutely correct. Because you remove the cycle, so it will become n-1 edges. You're absolutely right. Okay. So you can do CD or AE if they are same numeric or value path. Choose one of them arbitrarily. Make sure they don't form a cycle. Okay. So we selected CD here. Then AE. So when you do AE, still no cycle. Okay. If you select BC, 5, it forms a cycle, right? So you select EF. So where is EF? That is EF. Did we get all the notes yet? Not yet. We didn't get. Did we get all the notes? I think we did, right? A, B, C, D, E, F. Yeah. Okay. So then you see the total weight of the tree, 18. Okay. Is there anyone who does not understand Kruskal's algorithm based on the animation that I showed you? Okay. Silence means you all understood, right? That's what I take it. Now, same thing, Prim's algorithm. Okay. So what I want you to do is, I want you to take Prim's algorithm. Please copy this, mentors, just like how you have done. Students, copy this picture on your piece of paper. Tell me that you are done. Once, if you have copied it, then you say yes. Then I know that you did it. 2 minutes to copy that. Wow, Jntuk is fast. Actually, I want to see yes from everyone, right? Okay. Select the shortest edge connected to that vertex. That is AB. Okay. Then select the shortest edge connected to any vertex already connected. Any vertex, remember that, not B. That means it could be A, it could also be B. But you have to select the shortest edge. So if you see the edge connected to A, it has 4. And if you see the 4 and 7, and then you have the edges connected to B are 5 and 8. Right? So out of the 4, 7, 8, 5, you select 4. So that means AE is selected. Okay. Now you have AEB. So you have to select the shortest edge connected to all of them. Visually it looks like what? D, right? EB. See that? So it's going to select that. Now all the vertices that you have selected, you have to look at all the edges connected to those vertices and select the shortest edge. Which is the shortest edge? Next one, DC, I think. DC equal to 4. Okay. There you go. So you got CAEBC and then EF. F inka F raled. So EF is the shortest. You get that? That's your network. See that?
You have called has put you on hold. You can wait or call again later.
Okay. Is that all clear to all of you? The total weight of the tree is 18. What did we get in Kruskal, the total weight of the tree? Was it 18 also? No one remembers? They could use different edges too. Sorry. Guys, mute yourself. Check out together or me. Use different edges because You have to choose edges of the same length. Randomly, you pick one of them. Okay. The minimum spanning tree, which is the length, the value is the same, but the spanning tree itself could be different. Okay. So when I gave you the graphs last class, remember, so I inserted these new slides in between. So I'm going to skip these things because we did that one. Okay. Okay, all this I covered. So here is an example of a minimum spanning tree one more time, a graph and one of its minimum cost spanning tree, right? What I want you to do, not right away, I'll wrap up my lecture today and then you can work on this particular slide. Slightly different slide. Again, apply. When something is good, it is worth repeating, right? Again, so that way we'll remember that, right? So now you know what Kruskal is, what Prim is. Take this graph and apply the same Kruskal and Prim one more time to this graph, okay? After I say I'm done with the lecture today, okay? Give me a couple of minutes. Maybe I'm done, I don't know. We'll check, okay? So again, here are the steps for Kruskal, okay? And then as one of the colleges pointed out, stop if n minus 1 edges. You already came up to n minus 1 edges, okay? Because you need to have an exit criteria, right, to come out of the loop. Okay, I have Kruskal example here and I have Prim's example here. Okay, I'm skipping them here because I wanted to go back and work on them, right? In every stage, since you're looking for the smallest edge that does not create a cycle, okay, you're beginning to merge the trees. So you start with one vertex tree and then you build in Prim. Whereas in Kruskal, you start with n individual trees, if you will, called a forest, and you start connecting them. Okay. Now, which one to use, right? I think somewhere here I said, yeah, see the one in the blue there at the bottom. Use Prim's algorithm when you have a graph with lots of edges. Why? Because you know that when you're talking about edge-centric, if you have a lot of edges, if you're starting with an edge-centric algorithm of Kruskal, think of it. You have to cover so many edges, right? You have to first sort them in the order of ascending. Then you have to consider each an edge till you reach n minus 1 edges. So if you use Prim, since you're starting with a vertex, the number of vertices is smaller than the number of edges, right? So it's easier to deal with vertices. That's why you use Prim algorithm when you have a graph with lots of edges. So do we have to memorize that? Probably not. You'll know that, right? Hey, if too many edges, Kruskal is edge driven, let's not use Kruskal. Let's use vertices, right? And the opposite of that, if there are a lot of vertices and less number of edges, then you go to the Kruskal's algorithm. Okay. I think I'm going to stop right there because knapsack problem is maybe take this picture and apply Kruskal and apply Prim one more time. That way your concepts are clear and you will feel confident. And we are done for today's lecture. Okay, I will hang on till as much time as required. Now I'm not giving you the steps of Kruskal and Prim. You already know that, right? Don't take the picture on the right. That's a minimum spanning tree, okay? It's unfair to take that. You apply the algorithm and come up with something. And don't take one as the vertex in Prim. You take maybe 5. Each group can select different random vertex, right? Doesn't have to be one only. Okay, continue. Ready, set, go.